I want to show introduction to nanocrystals. So, firstly, we know that in the universe there are only three states of the matter: gas, liquid, and solids. So, we will focus on solids. So, today is not the time for gas and liquids. Solids we can separate into amorphous and crystalline. And again, we will limit our attention to crystals because it's topical.
Okay, I will just say. Tad šeit viņš stāsta, ka dabā ir gāzes, šķidrums vai cietas vielas. Cietas vielas iedalās amorfās vielas vai kristālus. Un šodien mēs par kristāliem runāsim.
So, what crystals are? Normally, crystals are supposed to be solid states in which atoms have fixed positions. So, and in crystals you can find a small unit called elementary unit, and if you took a look at other places of crystal, you can find the same unit everywhere. So it means that you can copy-paste or translate this unit crystal to 3D dimensions. So this is what normally is supposed to be crystal.
Jā, kristāli tur atomi sakārtot tādā secībā, un tur tie posmi atkārtojās.
So the next question is how to grow crystals. So in the nature they can grow by themselves, but normally people found specific technologies how to grow crystals. So firstly, so you can take some material, you can put it in a special crucible, and then you can heat it up to high temperature and melt it. And then you can put some holder, and you start crystallization. When you take the holder out of the crucible, so you have crystal, and at the end, so from the melted stuff you can get crystal.
Tad viņš saka, viens no veidiem, kā tos kristālus iegūst, ir sākumā to materiālu sašķidrina, un tad viņš palēnām kristalizējas, viņš paliek augstāks, un tad viņi kā velk uz augšu, un tā kristāls veidojas.
So this is another I will try to start this animation here.
No, cool.
Yeah. So we put some stuff in crystal in quartz ample, and we put it in a heater. Heater has a gradient of the temperature, so the temperatures are different in different ranges of the heater. So finally we have melting and crystallization. When we go from high temperature to low temperature, then we remove it from the heater, and we can have crystal inside the ampoule.
So this is the second method, yeah?
This is the second
Otra metode ir tā, ka viņi ieliek to materiālu tur iekšā, un tur ir tāds temperatūras gradients, kas sākumā kļūst karstāks, pēc tam vēsāks, un sākumā viņš izkūst, un pēc tam viņš sāk palikt cietāks un kristalizēs, un tā iegūst atkal kristāls.
So, next question. How to recognize crystals? If you have two crystals and you look at them, so you don't know if they are the same or maybe they are different. So, the question is, are those crystals the same? It's quite difficult to do that by your naked eye, and people found a way how to distinguish crystals from each other. So they use specific...
one minute, yeah.
Okay.
You can take it out. Okay. Ienāciet iekšā, mēs to lekciju turpināsim, un tad pēc tam būs es pasaukšu, kas tur tālāk. Jūs esat no kurienes? Mācieties iekšā. Tātad šeit būs viena lekcija, ko jūs esat dzirdēt, pēc tam jūs varat iest uz 4. stāvu, ja? Tas ir laikam 6:30 tas būs. Šeit tagad lekcija ir par nanokristāliem. Šeit mums ir viesis zinātnieks no Ukrainas, Romāns. Viņš stāstīs angliski, viņš stāsta par nanokristāliem, kā viņus audzē, un tagad bija lekcijas vidus, ja, un tad viņš stāsta, kā šķirt kristāls, kas tajā kristālā ir iekšā. Un tad šeit viņš saka, ka izmanto tātad spīdina gaismu, un atkarībā no atcerotās gaismas iegūst kaut kādu dažādu spektru, un tas nozīmē tie dažādi kristāli. Okay.
So, for recognition of crystals, normally is used X-ray diffraction. So, it's something like you can observe in every day. When you take light, you put it into the mirror, and you have reflection. And because of this reflection, you can recognize which kind of crystal is. Because so normally in practice, so you have X-ray source and you have X-ray detector, and X-rays fall onto the sample, and then you can measure the detection.
Okay,
so,
jūs saprotat, vai?
Yeah.
And in this case, that's important to know the angle of theta, the incidence angle, and then the detector measures angle called 2 theta. So we measure theta and 2 theta using this technique.
Okay. Labi, es nedaudz paskatīšu to zinātnisko daļu, kas Kodēļ tad ir tas kristāls tur stāv, kā jūs redzat, tas piemērs, un tad ir X stari, un tad viņus, tie rentgena stari, viņi visu spīdina virsmu, un pēc tam skatās atcerot to staru kaut kādā dubultajā leņķī.
So this is the industrial X-ray diffraction device. So this is X-ray source, this is X-ray detector, and this is a sample holder. So finally, each crystal produces peaks. So we measure in peaks to theta position versus intensity, and then there is a database, and you can recognize this peaks position with the material.
Jā, I will explain, jā. Un tad no tās grafika iegūst, piemēram, kāds signāls atkarībā no tā leņķa iegūst šādu ainu. Un ir zināms, ka katram kristāla veidam ir dažāda aina, no tā var pateikt, kāds tur tieši ir bijis kristāls.
Next question is how to recognize crystal size, because crystals can be different. So there could be single crystals, it means big crystals with good periodic structures. There could be polycrystals, so when you decrease the dimension of the crystal, so in crystal, so you decrease the volume of the crystal called bulk, and you have both surface and bulk. And the next one is when you decrease crystals to very small dimensions. In this case, the most important will be surface of the crystals. So these crystals with very low dimensions, about nanometers, so-called nanocrystals.
Jā, es paskaidrošu. Tātad kā tie kristāli var būt dažādi, viens tas monokristāls, kur ir tā struktūra liela, un citi, kur ir, piemēram, mazākos izmēros viņi sadalās, un tie mazākie ir saucās nanokristāli.
So, to estimate the crystal dimensions, we use electron microscopy. So, there is a scheme of scanning electron microscopy. Using this technique, you can observe what is the crystal. So, in this case, electron beam sputters electron beams. Electron beams produce electrons which hit your sample, and you can manipulate the electron beam using focus lenses, and the scattered electrons from the surface from your sample can be collected by a special detector and then analyzed, and you will see the structure of your nanocrystals. Later I will show some images.
Jā, tad viens no veidiem, tad elektrons spīdina uz kristālu, un tad skatās no atstarotās signāla, kāds, piemēram, ir izmēri tiem kristāliem.
Another way is transmittance electron microscopy. So this one is based on reflectance of electrons, but transmittance electron microscopy based on transmission of electrons. So the principle is the same. You analyze the electrons which transmit across your sample.
Jā, un otrs veids, kad elektroni iet cauri tam paraugam, un tad jūs redzat citu ainu.
So this is example what we normally have measured. So this is an image of organic nanowire, which is coated with thin layer of zinc oxide. So the structure, the core is organic, and then you have layer of you have thin nano layer on this nanowire. So if you take a look these samples and investigate it with SEM, you will see that these nanowires have shape about 300 nanometers, and the length of these nanowires about 1 micrometer. This is what we managed to do with SEM. With this, with transmitters electron microscopy, we can have better resolution, and we can even see single grains, single crystallites. So this dimension is about 9 nanometers, and if you take some analysis, you can calculate the number of the particles, and you can make distribution. You can calculate average grain size, and you can calculate how many how many crystallites with 9 nanometers, how many crystallites of 4 nanometers you have in the samples.
Okay, tātad šeit ir parādīts, tātad viņi ir tādi tievi gari, tāds materiāls, kreisā pusē jūs redzat, kā viņi atstarotais izskatās, bet jūs nevarat apskatīties, kāda tur viņiem struktūra. Un labajā pusē tas ir caurizgājušais mikroskops, te jūs redzat tam vienam diegam tie sāni, kādi viņi izskatās, tur jau parādās, ka tas nav kristāls tieši apkārt, bet tie nanokristāli, kā tādi gabaliņi, tos ar to izmērus noteikti.
So, another important information is a relief of your nanocrystal, or a relief of your surface. So, this one is flat, but if you go to nanoscale, you can see that it's not flat, because what we see is limited by our eye. There is a special technique called atomic force microscopy, and this technique allows to measure nanorelief of our surface. So it is based on special tip, which is very sharp, and the end of the tip is very thin. So when we the sample is held to the piezoelectric scanner, so we can move the sample, and the tip is located on the surface, and it repeats the every relief of the surface, and then we measure it. We measure the changes of deposition using laser and detector. I will show you how it works.
Ja šeit ir cits aparāts, kas mēra tieši tam nanokristālām virsmu, un viņš tāds, ka viņš slīd pa virsmu, un tikko virsmā ir izcēlns, tad viņš paiet uz augšu, atstarotais gaismas stars uzreiz noliecās, un tad var redzēt tas izmērs.
So it doesn't work.
Jā, tas video nestrādā.
Normally this is so this tip oscillates.
Jā, tad
and if the distance between surface and tip are too high, there's because of the forces between the tip and the surface, the tip goes towards the surface, and laser can calculate these changes. So here, what you can measure using atomic force microscopy. This is like 2D dimension, so the color is like a map. The color means height in z-axis, and of course you can make 3D plot, and you can see what you have according to.
Jā, un šeit no tā elektronu spēka mikroskopa jūs varat redzēt to virsmu, kāda viņi izskatās. Tad vēl prezentācija 2 minūtes, un tad jūs varēsiet tālāk. Jā.
So normally you need X-ray diffraction, electron microscopy, and RFM to calculate all about your nanostructures.
Jā, šīs metodas tad izmanto, lai visu noteikti.
And I will briefly show you our recent approaches. So here you can see SEM images, electron images of nanolaminates. It means that we deposited 2 different materials, layer by layer. The thickness of each layer is 10 nanometers. So 2 materials, aluminum trioxide is dark colored, and zinc oxide is white colored. So you see, first it was aluminum trioxide, then zinc oxide, then aluminum, then zinc.
Yeah.
So, and here we analyzed what we deposited using this technique. And these peaks show that we have zinc oxide. These peaks, so we didn't see aluminum trioxide because it was amorphous. So no crystalline structure was inside. So therefore, in X-ray diffraction, no peaks related to aluminum tracks.
Jā, un tā, tagad pēdējos slaidos viņš parāda, ar kādu zinātni viņš nodarbojas pašreiz. Redzat, publikācija apakšā uzrakstīt 2014. gads. Tātad tur ir slāņi, nanoslāņi, ko klāja vienu virs otru, un tad nosaka, kāds ir, piemēram, tas materiāls bijis, vai tas atbilst tam, kas bija plānots. Jā.
So this is surface morphology.
Jā, šeit ir tieši priekšā paraugu, ko viņi ieguva.
And so within the years, we can see that the change of the nanocrystal, the change of the size of crystals decrease. So it started with millimeters, then to micrometers, then to nanometers. And nowadays, all modern devices use nanotechnology, nanocrystals, cell phones, computers. So people found different another applications. And now the most important applications are sensors, nanochips, nanodrugs, and solar cells, because we can use it in every day, and so it works for social growth of our community.
Jā, tad viņš saka, ka kristāls izmanto dažādos pielietojumos, un kādreiz redzēt, tajos gados izmantoja tur milimetrus, mikrometrus, un tagad izmanto nanometrus, tas dažādās iekārtās, piemēram, saules baterijās tiek izmantots, un tad tas arvien vairāk tā tiek izmantots.
Okay.
Labi, paldies par uzmanību.